is a special day. First of all, we have amazing speaker, Svetlana Meissner. She's big professional in this area, believe me. And it's our last block from all these 16 weeks journey AI Math Club. And today we start week 13, probability basics, and our topic events, random variables, distribution. So let's start.
Okay, these some slides also from my lectures, and because it's just introduction, will go and look at the straight at the demos to have these basic understanding how we are moving from numbers to random numbers and distributions. We have this next, okay. So why we also need this, and how we start. And you can imagine that we can write x equal 1 or 2. Then we assign some variable a number. But now you can just imagine something like a black box, and we are asking this black box, oh, give me the number, and the black box give you one number, and the next time you ask the same black box, it give you the next number, and then one more number. And then these black box, can we say this something, so object that give us the distribution of numbers. Now like you say your variable is not like equal one specific value, but it's the collection of variables. Like here, so you see generate random numbers x1 to xn, and this whole collection we explain as a distribution, and then we use different mathematical methods to describe, so like this black box, that this specific black box produce these numbers, and these numbers, if we can put in how many from different value, like again this distribution and classical distribution, this is the het normal Gaussian distribution. And the mathematical method that we are describing after that, this distribution, then we're using again this estimate the mean of x, so this middle value from this distribution, and then we also can use different parameters to describe how big this distribution from this to this, or again mathematically describe different kinds of distributions. So like so here. Again, stochastic, now we are saying not a variable, it's a stochastic variable. And stochastic variable, it's a collection, like here x, 1, 2, 3, so different. And then if we are plotting this histogram, and you see at the bottom, then this value correspond from perhaps to, or it's just the, we are starting to generate these numbers, and it's how many numbers we have generated in this picture. It's 1,000 numbers. So from this black box, we ask, give us number, and so 1,000 times. And every time we've got some numbers, and here on y-axis, this is xy, explains that was the value something around the 10, but that was sometimes 2.5, sometimes 17.5, and from all these different numbers, then we can, to the right, we see this distribution function. So this is x, and how many we've got at 10, so most because it was distribution around the 10 perhaps, and then we've got also to the left, to the right, different numbers. So we've got not a normal variable, but this stochastic variable that have this distribution connected to these variables. And this actually very, very useful, because it's also, if you now perhaps very modern to go in this direction of quantum computing. Quantum computing also produce not only 0 at once, but all these between numbers. And you also can think about these like stochastic variables that produce quantum computing. And then you need the specific mathematics to deal with these kind of variables. And here I just skip the math. This is, again, you can use distribution function, then you can use normalization, you can calculate momentum from first, second, and so on. So just this average number, variance, and for the mathematical methods. And just these a little bit here charts, and we'll go to Python. And here, actually, these function or mathematically they look like, so to the left you see it's a little bit so complex. In the chart it's much easier just to draw, like again, these kind of distributions, but mathematically that wasn't very easy to calculate this. The Gauss, I think, was the first calculated this one for specific normal distribution, and then we are just having this different distribution. Here, examples, binomial distribution with different, again, parameters of these binomial distributions. And again, you think about having this black box, asking this black box to give you numbers, and then you put in these numbers in this histogram, and you then compare, oh, now this distribution, it look like normal distribution, or this distribution is look like perhaps this binomial distribution. And then comparing this kind, how from your experiment, how it looked like, and it's here also some Poisson distribution. Perhaps it's look like this. Then you have this connection, you have your experiment, your data, you find the corresponding distribution, and after that you just starting to use the whole mathematical process or whole mathematics that already known about these kind of distributions. So here's a binomial on there also connected if some sum of parameters, so very big, or n so constant, big M and n are much bigger than ones, then one distribution can go to the another distribution, and this kind of binomial distribution you could so approximate perhaps with normal distributions. So then or binomial distribution could be for the specific, again, parameter goes to Poisson distribution. So let's go then some examples. I also here started a Colab, and I also in Colab we're using, again, making these perhaps bigger. So here I just write for Gemini. So I study randomness and probability basics. Can you illustrate this concept in Python? And here we've got, so in Python, we are using this random. So also we need to import some libraries, import random, and this random's just library random choice, head and tails. And if we run just this part of code, so copy it, so go to, so I paste it already. So here, then I run this code, and we have, so this, I've run the code, we've got tails. So then we can run again. Oh, now we've got heads. And it's, again, just playing with these random numbers, head or tails. So what else we have? This is, again, playing with this or rolling a die. Again, here in Python, we can import this random, and then we can call the function random rand distribution 1 to 6, and then print die roll, and then we can go. So let's copy this one and also see how this works. So I'm adding here one additional cell. Let's run this cell, and we've got 2. We can run again 2. We can run. So again, now we've got 6. And again, it's just playing these games. what else is interesting? Let's again look at these further possibilities. So calculating probability. So the next part, to illustrate probability, let's simulate rolling a die many times and calculate the probability of rolling a specific number. So for example, so Fx, then we can again copy this part of code. So after that, I'm also adding, so here, additional cell, spacing here, and then I can run this part of code. So now we are again generating this number 1,000 times, count of 6, how many times we've got this 6, and then for this loop here, calculating, so every time rolling the dice and calculating how many times we got the 6, and then we have here this probability of rolling a 6 is 1.772, and also the probability of the dice 1/6 should be 1/6, and it's also the very similar number. But if you think of this, just rolling the dice, then this would be also rectangle distribution, because all of these 1 to 6 would be, if the dice, the right dice, not something wrong with the dice, for the right dice, it would be so 1/6, what we'll actually get here. What is this interesting? So next part, we can think about randomness and computer. And here, to demonstrate this, we are using this seed. Or usually, if you are experimenting with computer, in the beginning of generating random numbers, you have to set the seed. And setting the seed means these also depending on libraries you are using, so in Python or other languages, there are every specific libraries to generate random numbers, or you can again call more specific libraries. But the main purpose that the computer, it's a program and it don't have randomness at all. And we are just saying it's pseudo randomness. And that's why if we set the seed, here, this means we are starting our random pseudo randomness with this number. And here, after that, it's no more, actually, no, it's still randomness, but not this right randomness. So here we'll take in here, I already copied this to again to demonstrate. So here, now I'm here, I'm importing again random, then I'm setting the seed. And then after that, I'm generating, so print, so sequence once, print random numbers. You see here random numbers, usually if you call this function, it's one random numbers from 0 to 1. And at the moment we have 0.63, and for these many numbers are after the point. Then we are a random integer, the next from 1 to 10, we've got 1, and a random choice from apple, banana, cherry, we've got cherry. And that was because we've set random seed to this number. So now I can, again, here, we'll go here, we are adding, so one code cell, and now I'm copying just this part of code. Copy. Now we are running the second time, and here we are having different random numbers from 0 to 1. Random integer, now it's 4, and from this choice we've got, so apple. Now I'm adding, so new, so here I've added new section, but now we've got again, and we are setting the seed again at 20 or at 42. And if we are again starting our sequence, that means that we are going back to this starting point. So now, so for experiment, we are first setting the seed. So let's set the seed, and then you see up to the complete numbers, all this sequence is the same. So here, like, so here, 0.063, and so 1 and cherry, and here we've got also 1 and cherry. And again, if we continue, or if we get reset the seed, 42, we always would get the same. Or at the moment, if we continue the next, then we will receive these numbers for and apple, because we've started the seed. So that's why the meaning of pseudo randomness at computer, if you know the seed, then all the numbers after that you have this following numbers. So that's why very important to see the differences about mathematical randomness and the randomness how we implement in computer. Oh, what is interesting one I have here also. So I've got now. So in Gemini now we see making it bigger. Using Gemini, also asking about some plots about the distribution. So I also asked about normal Gaussian distribution, and we can use this code. And now we just calling also libraries matplotlib for the plots, and Seaborn also for colors, and NumPy to generate again these random numbers. This NumPy is the part that would generate random numbers for us. So then we are adding again new code, putting this part of code, and at the moment it's running the code to see again the charts I showed you before, and now we see these are the blue line, it's the mathematical line, and these are distribution, so numbers, the values that was generated. So here with these numbers with specific, we've got again 1,000 numbers, 1,000 numbers randomly was generated using the specific distribution, normal distribution, at the mean with 0 and the 0.1, the variance, standard deviation. So here you see this 0 mean and standard deviation. So you define this, and after that you can call NumPy function random normal with mu, sigma, and how many numbers you are generating. So in this experiment, and then you are calling just this plot function that help you put the title on the axis, and so just to see this distribution, so normal distribution. And this normal distribution describe also many processes that we have in our life, describing, for example, in demography, so the distribution of perhaps people for the specific age in the city, distribution also that so usually coming to us in many also social processes, or again we can use this mathematics to describe different so approaches. So then let again take here, we've got this one here again, some additional binomial distribution. If we put in here, also running this code, and we also got, so here binomial distribution, so number of successes, and again, so frequency. This is the different part of distributions. And then we've got, let me see, in what was also interesting, working with concepts. Just a moment. Good. It's already disappeared, but we can ask, give me some interesting problems with probability. Distributions. Okay. So the birthday paradox. So very interesting. How many people need to be in a room for there to be a greater than 50% chance that at least two of them share the same birthday? And again, we can calculate, assuming 365 days in the year. And again, we are coming after to assume that birthdays are uniformly distributed, but this again here at this moment started all what we can assume. And actually, if we will see that during the years also it's not uniformly, very interesting also problem in demography that the birthday not equally distributed, but assuming this, and then we can also calculate. The result is surprisingly low, which is why it's called a paradox. It demonstrates how our intuition about probability can be misleading. And this problem involves calculating the probability of the complementary events. No two people sharing a birthday, which is often a useful strategy in probability. And here it's also show us, so this is concepts, and then probability of complementary events, so calculating that if the probability for something is P and A, then all the other we are calculating as 1 minus P not, so we can also say that all the others not A, and then 1 minus this, and again this is P of A, and this combination. And then we need also the concepts of combinatorics and permutations to get this problem. Here, the German tank problem, also the problem during the World War II, the Allies captured a number of German tanks. Oh, okay, I skip military problem at the moment. It's just interesting that Gemini suggests this. Or the poison process calls at a call center. Okay, this also very interesting problems. So a call center receives an average of 10 calls per hour, and the calls arrive independently and constant rate. And then we also can calculate what is the probability of receiving exactly 15 calls in a given hour, or the probability of receiving 5 or fewer calls in an hour. And it's also connected again with these kind of problems to put the right amount of working persons, or again to calculate the so what needs, so to calculate the possibilities, what we need of what kind of resources we need to use here. Let me see whether we have one very interesting problem on light bulbs. I'm not seeing this one. The one of the very interesting, the moment not a very interesting problem and wasn't solved in the beginning was about the choice at the event. If you have these 3 doors that are closed and the event guide say you can choose one of these 3 doors. Let me see. I'll also ask. Can you explain the problem with 3 doors experiment? We'll check. But again, and behind one of the door, perhaps it could be a car that you can win, and all the other 2 doors just have the goats or something not interesting. And then Monty, whole problem. Just let me see whether it's got the same. It's already again, and the host ask you, so now you can choose one of these 3 doors. You pick up the door, and the host not opening you and saying you have won or not, are just asking you, the host opening one of the door that definitely don't have the car, the door have the goat, and the host is asking you whether you stay at your choice or you would like to change. And then you, to solve this problem, you need again to calculate the probabilities for the possible event. And before, everyone thought, oh, a probability 1/3, so every door is the same probability. But the moment that the host opening the door and reveal you that this door doesn't have the car and asking you, then you have to change your choice. The probability, if you are changing, so if you're going to this new, changing the door, then you would maximize your probability of winning the car. So the question is to maximize your chance of winning the car. So should you stick with your original choice or switch? And so if you would calculate really the probability, then right calculating that the better that you are switching the door for your choice, your probability will increase at this moment. So we are so ready. So Anna, so how do you think?
So yes, biggest things, I can stop the recording, and of course